Hi. I'll give a background on all these acronyms we have: MDP, MAB, MCTS. Then I will discuss these algorithms, putting them together in some unifying perspective, discuss two new algorithms, MPA, UCT, and MaxBRUE. Yet another new algorithm, MaxBRUE Plus, and you will be fed with acronyms by the end of the talk. So, you all know what MDP is. Just briefly, we talk about finite state space MDPs, finite set of states, finite set of actions. Actions are stochastic, and they're given by this conditions, by a simulator, perhaps, that simulates conditional probability distribution of the transition functions and the reward function that can be, that is Markovian, but can be arbitrarily complex. The objective here is to optimize expected performance over h steps. And we're looking for algorithms, so we're focusing on algorithms that are smoothly improving the outcome over time. And we focus on online planning, so we only care about the action recommendation for the state our agent is currently at. Anytime means that we don't know how much time we have for planning, and we can interrupt it at any arbitrary point of time. Strong anytimeness stands for your algorithm cannot be sparse sampling, which means the performance should be improving smoothly over time in small time quants. And forget about the formulas. We evaluate the performance of the algorithm by what is called simple regret, which basically is the difference in quality between the action you recommend and the best action that can be recommended. And the notation we'll be using throughout the talk, SH, stands for world state S with H steps to go. In finite horizon, it does make difference how many steps you still have to live. Now, MAB stands for multi-arm bandit problem, one of the canonical problems in OR research. And basically, MAB is a nano MDP, like the smallest MDP possible. It has only one state. The horizon is 1. All your actions take you back to the state you are in, and the problem is that the actions give you stochastic rewards, and you don't know this induced probability distribution ahead of time. So you want to kind of learn what is the right thing to do. And algorithms for planning in multi-arm bandits employ two strategies. It can be actually one strategy that fills these two roles, but in general, it has to decide how to explore different actions. And okay, given that now I'm stopped and have to give a recommendation, what will be the strategy according to which I will recommend the action? Many of you are familiar with what is called the upper confidence bound strategy, used by, for example, UCT algorithm, that is basically Chernoff bound inside out. This strategy can be used for exploration, and basically it says that you take an action you sample action that maximize additive combination of empirical quality of the action and some exploration factor. So the actions will not start for too long. And in learning while acting setup, close to what Peter was presenting in the previous session, we are interested in optimizing accumulated regret over time. But in setup we are in, we don't care about cumulative regret because we plan, we use simulator, and we don't pay for the actions we run on the simulator. It's like think that Las Vegas sends you home simulators of the slotting machines, okay? And you can practice as long as you want. You are not using real money. The real money you will be using only when you go to Las Vegas and use the recommended actions you employ. Now, Bubik et al. Investigated simple regret optimization in multi-arm bandit problems, and the table compares the rate at which the recommendation improves over time. The rows stand for two different exploration strategies. One is uniform, just sample actions uniformly or in round robin, whatever you prefer. And the other strategy is UCB. Alpha stands for the constant that used to balance between exploration and exploitation. And for recommendation, there are two policies. One, EBA stands for empirically best action. So if you are stopped, you just recommend action with best empirical quality. And MPA stands for most played action. With uniform, most play action doesn't make sense because, well, there's no meaning for how many times you sample action. You just sample them uniformly. With UCB, it does, and in fact, for properly chosen value of alpha, it is much more logical to bind UCB with MPA rather than EBA. However, notice that again, in both cases, UCB converges only at polynomial rate, while uniform with EBA converges an exponential rate. Now, that's not the whole story. When you look at the bounds and the dependency on various parameters, it shows up that uniform plus EBA is a bad idea if the time you have for planning is relatively permissive. And UCB alpha with EBA again is more with MPA is more logical when the kind of gives you better bounds when the planning time is moderate. Kind of it can get lucky, and in expectation this luck pays off, while uniform doesn't believe in luck. So that was the outcome of analysis of Bubeg et al. In 2010, and so we are going back to MDPs, which is from nano MDPs to general MDPs. And here is a very, very brief generalization of a family of algorithms called Monte-Carlo tree search algorithms. And one interesting thing about them, that there are no trees there. And so again, the algorithms go in loop, and at every iteration of the loop, they do two things. One, they issue a trajectory called rollout in state space from the current state on, using this or another sampling strategy. Given that rollout, the algorithms then update some data structures they maintain, growing tree, counters in the table, whatever you want. And that's what they do. Once they are stopped, they issue recommendation. Here, for example, the recommendation is corresponds to empirically best action. Okay? So again, the rollouts are just sequence of state, action, reward, state, action, reward, state, action, reward, with the first state in the chain being our current state for which we are planning. Now, so it's history a bit. In 2006, Coxes and Shepeshvari introduced algorithm UCT that in our terms do the following. The rollouts are issued according to the UCB strategy, so employing this UCB formula at every state visited on the way. Now the update. What is updated? So for update, we have to answer three questions. What to update, with what information, and how. What we update in UCT is all the nodes along the rollout. So we're going kind of backwards along the rollout and update the information. The updates are done with the rewards collected by that sample, that rollout. And the updates are what is called Monte-Carlo backups, which is maybe not very successful name for just averaging the samples. Okay? That's what UCT does. In 2012, Zohar and I suggested a different algorithm called MaxBRUE. Rollouts in this algorithm are issued according to the uniform distribution. Okay? So no cherry picking, you just uniformly explore your state space. Updates are different from UCT in the following sense. First of all, what we update, same as UCT, we update all the nodes along the rollout. But when we come to update a value of an action at a state, we issue for that purpose a separate rollout, denoted here by a raw head, the tilde, whatever. And that rollout is not issued according to uniform distribution, but according to best empirical action. So we just issue additional rollout by following the best empirical actions. And the updates are done by MC backups. And in contrast to UCT, that achieves only polynomial rate convergence over time, MaxBRUE converges at exponential rate. Another algorithm, closer to UCT than to MaxBRUE, was suggested last year by Thomas Keller and Malte Helmert, and it's called MaxUCT. Basically, MaxUCT is UCT, because everything, the first two rows are the same, but the updates are done a la value iteration. So the updates are Bellman-like dynamic programming updates. We go back on the rollout, and we want to update the value of the action. We look at the successors of this action, take the empirically best actions, take the empirical values, back propagate it to the node. And importantly for what comes next, here the algorithm should estimate not only the values but also the transition probabilities. Because to perform Bellman-like backups, you have to use the transition probabilities of the actions. If you don't know them because you are giving a simulator, you have to learn them. If you know them because you have a declarative description of the domain, you are in illusion that you are in better position if you'll use this information. But actually, and I will take it offline, that will be a mistake. Okay, so first we say, okay, in multi-arm bandit, we have this exploration strategy and recommendation strategy. To what it corresponds in MDPs? Well, actually, the correspondence is quite straightforward. Exploration strategy in MABs corresponds to rollout issuing policy in general MDPs, like in MCTS, and recommendation strategy in MABs corresponds to the update strategy in MCTS. And now, when you look at, so the rows again correspond to exploration, to rollout strategies, and the columns correspond to update strategies. You will see that, well, BRUE is exactly uniform exploration, EBA recommendation, and MaxUCT of Keller and Helmert does UCB1-based exploration and EBA-based recommendation. In that respect, UCT stands in a very strange position. It corresponds to UCB-based exploration and UCB-based recommendation because they do not distinguish between these two strategies. They use one strategy along the algorithm. And in MABs, it is a very, very weird thing to do, which suggests that it's also a very, very weird thing to do in MDPs in general. Okay? This combination of strategies for MABs is super, super weird. Okay, now once we have a table now, okay, let's start filling in. Now, again, as I said, uniform with MPA is nonsense. Most played action while with uniform exploration is pointless. It says nothing, how many times you play an action. So, two algorithms we'll be discussing are, very shortly actually, are MPA UCT, which is basically UCT with update strategy being based on most played action and not on empirically best action. And again, we try that because, well, it gives us better bounds. Why it gives us better bounds? Because it also gives better bounds for maps. And MaxBRUE corresponds to BRUE, which is uniform exploration, but then the updates are done with dynamic programming backups. Those who were at the workshop on uncertainty in planning kind of got a pick on the next work that will be presented in ICAI, where we dive into question of dynamic programming updates versus Monte-Carlo backups more closely. Now, so again, MPA is just UCT with MPA backups. And MaxBRUE is BRUE with DP backups. Now, why we are doing that for? We want to get algorithms that perform better both formally and empirically. And for MaxBRUE, we came up with a bound on its convergence. Again, unlike MaxUCT that converges in polynomial time only, MaxBRUE, like BRUE, converges at exponential rate. In terms of bounds, the bounds here, so you say exponential, E2 minus, well, that's exponential rate, that's good. But the constants there are a bit hairy. For those, however, for those two people that are familiar with constants for BRUE, these constants are bold. So these constants are much better than what we have for BRUE, which kind of suggests that DP backups are better than Monte-Carlo backups, but it's wrong. Why? Because these are only bounds. Be careful with that. Analysis of DP backups is logarithmically easier than analysis of Monte-Carlo backups, and so please be careful with that. And then, when we looked at MaxBRUE, we realized that in general, when you dig into Monte-Carlo algorithms, you discover bonanza of interesting questions. We don't know a lot about these algorithms, despite the fact that they are used all over the place. And think about that. So again, we're talking about DP backups, okay? Now think about the node and an action that we can apply at this node, somewhere in the state space. And we estimate the value of this action. Now, inaccuracy of this estimate can come from two sources. One, inaccuracy in estimating the values of its decedents. Two, inaccuracy in estimating the transition probability function. And ultimately, we would like to balance these two. And in fact, this is precisely what sparse sampling algorithm achieves. It makes sure that all the nodes contributing to the overall evaluation are sampled exactly the same number of times in expectation. So both nodes and their decedents are sampled exactly the same number of times. And this is the best way to achieve this balance. We cannot do that because sparse sampling is a contract algorithm. You activate it, go drink coffee, and hope it will finish at some point. What can be done, however, is the following. So again, if Monte-Carlo algorithm, deeper the nodes are farther from the current state they are, less you sample them. However, it can happen that a node deeper in the tree is sampled more than its ancestor. Why? Because the state spaces are not trees. It can be the case that some node has lots of paths to it, much more than the number of paths to each one of its ancestors. And when you come to estimate his ancestor, and this decedent was sampled much more times, this sample is pointless. Just stop it. Stop the sample, say, okay, let's try again. Let's try something else. And that is the essence of the plus in MaxBRUE. Run your sample, but when you get to a point where your decedent is estimated more frequently than you, stop the sample, go back, save time. And it formally gives exactly the same guarantees as MaxBRUE with less sample complexity. Don't read the slide, please. It's everything in the paper. The bottom line is what I said. And here is the picture. Lower is better. So x-axis is just number of iterations. And y-axis is simple regret. So fast state goes down, the better. And the results are on sailing domains, 20 by 20 and 40 by 40. And you see that max UCT performs worse than MPA UCT. Again, on a particular domain, everything can happen, right? But these results are in line with bounds. And MPA UCT is slower than MaxBRUE, and MaxBRUE is slower than MaxBRUE Plus. Because again, it's the same number of iterations, but MaxBRUE makes cheaper iteration. It stops them on the way, so okay, forget about it, let's start from the beginning. So in terms of estimation, it does well. Now, I will skip these graphs, just will summarize you the outcome. If you remember at the beginning, I said, for MAB, the bounds that we know so far suggest the following. If you are really, really restricted in time, UCB exploration is presumably better than uniform. Again, you can get lucky, and with this number of samples, luck is good. But once your budget grows, abandon UCB, switch to uniform. And the results that we have on IPPC domains confirm exactly that. On smaller instances, you can either fix the budget or fix the instance, whatever. But if you fix the budget of samples on smaller instances, uniform outperforms. Once the instance grows, UCB-based exploration performs a bit better, but again, better doesn't mean well. So again, it can be that uniform is completely lost because it has no enough samples, and UCT from time to time can get lucky. So it's quite possible that we're on the way to devise better algorithms that will actually perform much better than UCB. There is no reason why UCB should be better than the right thing to do. It's just we don't know yet what is the right thing to do. For moderate budget. For large budget, we know exactly what to do. So to summarize things, the main point of this paper is fruitfulness of looking at Monte-Carlo research algorithms for MDPs via the lens of what to do with multi-armed bandits. And if you find that if you systematically learn from what is good in multi-armed bandit and try to export it to MDPs, it pays off. And in some sense, UCT is a very strange way of exporting our experience in multi-armed bandit problems to MDP. MaxBRUE gives best bounds so far among all algorithms we know on the convergence rate, but as I said, bounds. A much deeper introspection we offer in ICAPS paper that was shown in the workshop shows that these bounds hide a lot because these are worst case bounds and worst case bounds. So they apply to uniform distribution, for example, for transition probability function, et cetera, et cetera. Who cares about uniform transition function? And they also, analysis of dynamic programming updates is way easier. I mean, you take two algorithms, as I said at the workshop, we have two algorithms. The only difference is here you do Feldman backups, like dynamic programming backups. Here you do averaging. And this algorithm can be analyzed in one page, and that algorithm takes you 25 pages and new concentration inequalities to prove. So, and it means that on the way, you make rough estimates like union bound here, union bound here, union bound here, union bound here, and these constants blow up. It doesn't mean that these are really best constants. MaxBRUE is, again, trick that improves the performance, and this trick stems from, going deeper into algorithm and thinking, what's the right thing to do? What really matters there? More deeper sample, it's always a good idea to continue with the sample. The answer is no. And again, the work on Monte-Carlo research, guys, is not only UCT. We know almost nothing. We all know very little about these algorithms, and it is a bonanza of interesting questions and great promise. So I encourage many of you to reread the books on probability theory and dive into this area. Thank you.
So we have time for one or two questions.
Have you done any experiments on how well, say, MaxBRUE does in combination with heuristics as compared to UCT with heuristics?
No, because usually when the answer is no, the reason is that we're lazy. It's hard to drive conclusions when you use heuristics because, the heuristic can change everything. What I can say, following our discussion at the workshop, that MaxBRUE is worse than BRUE. Forget about the bounds. Once your problem grows, either in branching factor of actions or in branching factor of states, or your transition probabilities are no longer uniform, Monte-Carlo updates pay off. And there is a reason for that. That is hidden by the bounds.
Okay. The reason I asked about this is since BRUE basically does this bold exploration, right? It could be that it actually performs worse in combination with heuristics because, well, heuristics give you some initial values that are presumably good, and then you what do you call them? You basically wipe them out with samples from these basically bold trials, some of which yield very low reward.
The answer is yes, but you should be careful. It's not clear what is the right way to employ heuristics in the context of BRUE.
Okay.
But you're right. If you know what's the right thing to do, why do you need MCTS in the first place? And the heuristics, can pay off, can hurt you. It depends. It depends.
Sure.
All right. Well, let's thank the speaker.
Thank you.